how can you realistically compare two values such as someone's weight on Earth and someone else's weight on Mars, or more realistically, how two people did on the same type of exam? So maybe someone took the MCAT in 2020 and someone else took it in 2019. And even though the total possible score remained the same, um, knowing that someone got a 23 and someone else got a 26, granted 26 is higher, but maybe that was an easier exam, you know? And so the value itself doesn't take into account difficulty. So how can you adjust or account for different difficulty levels? And one way to do that is by standardizing the data. And so that's what this topic is about, is standardizing data. You're going to learn how to transform data values into a standardized value known as a z-score. You'll be able to interpret and compare z-scores. And you'll be able to use a table, the standard normal table, or oftentimes I might refer to it as the z-table, in order to find probabilities with respect to z-scores. So that's what we are tackling now. Now, z-scores are normal or standard normal random variables. What does that mean? Well, normal means bell-shaped, like the pictures that you see on my screen. So they're symmetric, they're bell-shaped, they're centered about the mean. That mean is mu, and they've got some spread. Now, being that they are standard normal, because normal just means symmetric and bell-shaped, but standardized or standard normal means that they are normal, they are symmetric and bell-shaped around the specific value of 0 for a mean, and have a particular variance or standard deviation of 1. So that's what standard normal means, is that they are normal 0, 1. So there is a difference between normal and standard normal, and that's what the difference is. Normal is mean mu, variance sigma squared. Standard normal is mean 0, variance 1. All right, so how do you get a z-score? Well, a z-score is a distance. It's just a distance in terms of a unit that you probably aren't used to. You know, most of us are used to distances in terms of feet, inches, meters, miles, you know, some sort of measurement like that. And now you're going to be learning distances in terms of the unit of standard deviations. And so that's going to be important to keep in mind, is that a z-score is not a standard deviation. It is a distance in terms of a standard deviation. So I am 3.2 standard deviations taller than that person. That is the type of distance we're going to be talking about. One way to do that is by the formula I've highlighted in blue there. And this is one that you would use when you have a single observation. So you have one person's height, or one dog's age, right? Or one child's head circumference. So if you have one measurement, you would be taking that measurement x, subtracting the population mean for that particular type of measurement. So all, my oldest child is 6 years old, and so all 6-year-old head circumferences, what's the mean of that? That would be mu. And the standard deviation of head circumference for male 6-year-olds would be what I divide by on the bottom there. But sometimes you may have more than one measurement. You may have a group or a sample of size n, in which case you're going to be using the second formula highlighted in yellow there, which is x bar, so the mean of that sample, minus mu, which is the mean of the population, divided by sigma with the subscript x bar. And that subscript x bar tells you that that is the standard deviation of the sample mean, which is given by this. And so it is the standard deviation of your population divided by the square root of the sample size. Now that comes from something called the Central Limit Theorem. And the Central Limit Theorem simply says that if you have enough data which depends on your resource. Some books say at least 20, some say at least 30. I'm going to go with at least 20 here. If you have at least 20 observations and you know the mean and standard deviation of, or variance, mean and variance of the distribution, then you know that the distribution of X bars is going to have the same center. So it'll be the same mean, but it's going to have smaller variability. It's going to be sigma squared divided by n. So that's pretty neat. And now this is informative, and it's unique because it's subtle in that it doesn't matter the shape of the distribution of the x's. So notice that nowhere in here does it say X has this type of distribution. It just says the mean and the variance are these, but X bar will be normal. And so that's important. That means that X bar is going to be bell-shaped. All right, so knowing that the variance of X bar is going to be sigma squared over n, that means that the standard deviation is going to be the square root of that, or sigma over root n. And that's where that boxed out orange concept came from. All right, so let's start figuring out how to apply these concepts, right? In the first problem here, we have a table of 5 people's heights. These are males. And in part A, it says that John is 72 inches tall. We want to describe numerically how John's height compares to the average for all males. Well, in blue above that, I highlighted that the average height for males is 70 inches. And so how does he compare? Well, he's 72, so he's 2 inches taller. Not too challenging, fairly intuitive. And that's exactly what I say here. 72 minus 70 is 2. And so John is 2 inches taller than average. Well, what about Rick's height? Rick is 65 inches. How does his height compare to the average height? Well, 65 minus 70 is minus 5. So that minus sign means shorter or lower. And so in this case, we know that Rick is 5 inches below or shorter than average for males. All right, so far so good. Well, how tall is the male that is 2.5 inches shorter than the average male? Well, 2.5 inches shorter, so that's going to be minus 2.5. And that's going to be with respect to the average height of 70. So 70 minus 2.5 is 67.5. And none of this really required a formula. But if you really like formulas on the left-hand side, all we did was we pretty much said, well, x minus mu gives us the distance or the comparison between an individual's height and the average height. All right, let's move on to number 2 here. It's working from the same problem, but we're just given a little bit more information. We're told that the concept of standard deviation takes the units of the sample data. Assume that the standard deviation of male heights is 2 inches. So that's the population standard deviation. How many standard deviations above the average is John's height? Well, John is, in part A, we got John to be 2 inches above average. And we know that the standard deviation is sigma is 2 inches. So that means that John is 1 standard deviation, because 1 standard deviation is 2 inches. So he's 1 standard deviation above the mean. There's a few ways of thinking about it. That's one of them. And I'm showing both of them here. So on the left side in black, I've got a more formulaic approach. 72 minus 70 gives you the distance in inches that John is with respect to the average. Divided by 2 is the standard deviation. And so 2 over 2 is 1, or 1 standard deviation above the mean. More conceptually in blue there, I'm showing that if you were the average male at 70 and you need to step standard deviations to get to John's height, you would take 1 step, because 1 step would be 2 inches, or 1 standard deviation is 1 step, and that would be 2 inches. And so that's a more intuitive approach to getting at the answer of 1. What about Rick? So describe Rick's height with respect to the number of standard deviations above the average or away from the average, because we know he's shorter. So over here, you could do the formula approach. You've got x minus mu over sigma, because this is one person's height. 65 minus 70 is -5. -5 divided by 2, because 2 is the standard deviation. And that's going to give you -2.50. So that means that while he was 5 inches below average, that is 2.5 standard deviations below the average height. Right. Intuitively, that is going to look like this here in blue with some green. So the average height is 70, and stepping 1 standard deviation to the left gets us to 68, because remember, 1 standard deviation is 2 inches. Another standard deviation to the left brings us to 66. He is 65, so we need half a step more, or half a standard deviation. So that's going to be 1, 2, 2.5 standard deviations down or to the left, which is why it's going to be negative. And that's all a z-score is. So whether you use the formula approach or more intuition, I'm okay with either, but I think a picture would be helpful so that it doesn't look like a guessed answer on any future quiz or work. All right, so what might we do with that? Well, let's move on to another example here. This says, recall that the average is a type of mean and that distances are usually computed with respect to a mean. Distances in terms of the number of standard deviations also require that the sample data are from a population with a bell-shaped normal distribution. In A, it says foreign students often need to take a TOEFL or test of English as a foreign language exam in order to study in the US. The 2011 TOEFL exam scores had a mean of 85 and a standard deviation of 3. April achieved a score of 92 on the exam. How many standard deviations above the mean was April's score? So this is another way of asking what is her z-score. So z-score is the individual score, which is an 85, minus the mean. Sorry, she scored a 92. I apologize. April's score is 92 minus the mean on that exam of 85, all divided by the standard deviation on that test, which was 3. So 92 minus 85, which is 7, divided by 3. And that gives us 2.33. So April was 2.33 standard deviations above the mean because it's a positive z-score, as long as you plugged in appropriately. A common mistake is instead of x minus mu, I see mu minus x, but it's always the observation first. But then you have this other student, a friend of hers, Yolanda, that took the exam in 2012 instead. And she did well. She got a 90. She got a 98, but the average on that test was a 90 with a standard deviation of 5. And so what was her z-score? Well, 98 minus 90 is 8. Divide that by 5, you got 8 over 5, and that is 1.6, I believe. So that means that Yolanda was 1.6 standard deviations above the mean. If you knew these two students, these two friends, and you just asked them what their scores were and you heard 98, 92, you say, well, the 98's better. But her exam was a little easier with respect to the mean because the average was 90 instead of 85, but a little more challenging with respect to standard deviation because there was more spread. In other words, there were more students that did well, but also poor compared to April's test with a standard deviation of 3, which means the scores are closer together. They're more similar. So by taking into account the difference in means and standard deviations, you account for differences in difficulty. And now we can say in part C, well, who performed better? Well, April was 2.33 standard deviations above the mean versus Yolanda's 1.6 standard deviations above the mean. So that means that April did better on the TOEFL exam. All right, so now we are going to tackle number 4 here. The weight of adult males are normally distributed with a mean of 172 and a standard deviation of 29. What is the probability that one randomly selected adult male will weigh between 165 and 190 pounds? So over here, we are going to want to convert to a z-score. Right? We're told that male heights are normally distributed, and so we want to convert these, or sorry, weights. This is weight. Convert these to z-scores. And so I want you to pause the video, convert it to a z-score, and also see how far you could get with B. And I'll be back in a moment. When you're ready, hit play. All right, let's continue and see how you've done. For part A, what is the probability that one randomly selected adult male will weigh between 165 and 190 pounds? Well, the P statement here I've got shown on top there. It's the probability that X is between 165 and 190. And that's what we want to convert into z-score. When you're doing this, you're going to convert both sides of X to a z-score, meaning you're going to convert the 165 to a z-score and the 190 to a z-score. And when you do that, what you should get is this. So you take the 165 minus the mean of 172, divide that by 29, the standard deviation, and you'll get negative 0.24. When you follow a similar path on the right-hand side with 190, you get 0.62. I'm not going to finish this off just yet to get an answer because we're going to practice in the next video what you'll need to do. But let's take a look at B. B says an elevator at a men's fitness center has a sign that says the maximum allowable weight is 4,700 pounds. If 25 randomly selected men cram into the elevator, how likely is it to exceed, the maximum allowable weight? So if you have 25 people that cram in, to know what the weight is, you would add up each of their weights. And so the probability statement here is the probability that the sum of X is greater than 4,700. Now that's new. We haven't seen that yet, but we know that if you were to divide the sum by n, the number of values that you had, you'd have a mean. So that's exactly what I did here. So the sum of X divided by n gives you X bar, and 4,700 divided by 25 gives you 188. And so now this is a probability with respect to X bar, not with respect to X. So that means you're going to be using the second formula that I had shown you earlier, all the way at the top here. You're going to use that second formula with the sigma over root n. So you've got 188 minus 172 divided by sigma over root n. So it's 29 divided by the square root of 25. And that will give you 2.76 if you plug in appropriately into your calculator. Again, we want to actually answer these probabilities. So in the next video, I'm going to introduce you to how to use the standard normal table and to convert from a z-score into a probability.